Next up, we have David Jens from University of Cambridge, who has interned with us previously, and we're glad to have him back here.
Hi everyone, thank you Ryota for the introduction. I'm going to be talking to you about some work I've done in collaboration with people here at MSR, with Katja and Sebastian, with my supervisor Miguel at Cambridge University, and with a fellow PhD student, Jerry Hron, also from my group at Cambridge CBL. We'll be talking about probabilistic modeling for exploration within temporal difference learning, a difficult topic within reinforcement learning that's only just begun to be tackled in a grounded manner. So just to begin with, a quick rundown of what I mean when I say reinforcement learning. Within reinforcement learning, we are focusing on an agent interacting with, and this is very important, an unknown environment. The goal of the agent is to obtain a high expected cumulative reward over some time period. Now the key here is that the agent interacts with the environment not just to receive a high reward now, but to learn how to receive high rewards in the future. Thus, all interactions of the environment, the agent has to balance exploiting what it already knows together with exploring the environment. The environment itself is typically modeled as an MDP, so that's a little formalism that basically says the agent's in a state, it carries out an action, it then proceeds to a next state and is given a reward. So that's kind of the model mathcal T here. And the goal of reinforcement learning, not in terms of the problem but the solution, is to find a policy, a mapping from states to actions that leads to the highest long-term cumulative reward, at least in expectation. So that's the expected sum of over rewards in, say, an episode of a game or in a lifetime of an agent. Many of you will be familiar with this screen. This was one of the advancements from DeepMind in 2013, combining deep learning with reinforcement learning and achieving kind of relatively good, in comparison to humans, performance on some 30-year-old games. Now this is cool, but there's one major detail here. For each one of the 50 games, they use 200 million frames. That is 38 days of normal speed playtime, or much, much, much more than a human ever could. And even would, sorry, not could. And even more importantly, they performed poorly on any of the games that required exploration. That is, where the goal of the game was not immediately obvious, where one needed to take multiple correlated actions in order to find the high rewarding areas of the game, or to proceed through multiple levels of the game in order to achieve some sort of reward, obtain a key to a chest, those sort of tasks, rather than tasks on which it did well, which is just plain shooting aliens, getting a high score. The way DeepMind tackled Atari is through what we know as model-free reinforcement learning. That's a set of methods which focus on translating dynamic programming methods, so recursive methods of computation, to a more approximate regime where function approximation may be used. So here, within model-free reinforcement learning for a scenario like Atari, the key quantity considered is the Q function. The Q function tells you, for a given policy, if I'm acting according to a policy, if I were to deviate from it for one step, what would happen? Would I expect to then get a higher or lower reward than by just following the policy? So the Q function tells me what's the value of, if I'm in a state, what's the value of taking an action just for this one step and then carrying on with my policy. Clearly, or not clearly, but it can be shown that if you start with just a fairly random policy, compute the Q value for it, then if at every step you take the deviation that improves your predicted value, you should improve the cumulative reward you expect to gain. And then if you were to make that your policy, if you repeat this process and iteratively compute a policy that's greedy with respect to a Q value, and then look at one-step improvements to that policy, under some technical assumptions, you converge to a good solution. The Q function itself is also computed recursively. This is kind of a temporal difference, the dynamic programming part of it. If we say at the end of the game, my value is 0, then the value before it should be whatever reward I expect to get plus 0. And so recursively working from the end of the game, given a data set, a fixed data set, you should be able to compute a Q value. The trick within reinforcement learning, however, is that this data set is not fixed. As you interact with the environment, you change what's in your data set. And when interacting with the environment, you want to use an exploratory policy that gets you data that informs you about what the optimal policy is as fast as possible. This isn't simple, but this is kind of the premise of the talk today. And specifically, we'll be looking at how to use probability and probabilistic models to achieve this. Okay, so just general exploration methods. The most trivial one used within the 2013 work by DeepMind is epsilon greedy. This means you take what you believe are optimal actions according to your current estimate of the state action value function. And every so often, with probability epsilon, you uniformly pick a different action. This means you are taking small deviations away from some kind of an policy believed to be optimal. This gets you a fairly narrow range of exploration in that the way you explore is not based on any belief over how good or bad these alternatives are. It's purely random, uniformly random. To build on this, the most immediate thing you might think is, indeed, let's figure out not just how good each action is on average, but how certain or uncertain we are as to its value. So we may prefer actions that we believe may be good and we are uncertain about, as these both may give us good cumulative reward over time and may allow us to learn more about the environment by decreasing this variance. So that's generally what are known as upper confidence bounds, and they rely on being optimistic. The upper confidence bound tends to overestimate the value of an action, state and action pair. So over time, you tend to explore all the state action pairs. This is a deterministic policy. Now, an alternative to this, which is no longer theoretically claimed to be better. A proof for it was actually disproved or proven to be wrong last year. However, seems to perform better empirically, is instead of deterministically taking the action with a high mean and high variance, we sample policies with probability, with our belief, with respect to our belief that they are optimal. This means that instead of deterministically taking actions we believe to be high variance and high mean, we are indeed more likely to take those actions, but it's a stochastic process. These policies end up being what's known as stochastically optimistic. They do roughly the same thing, just with a bit more stochasticity in it, and empirically in a lot of scenarios end up converging faster. This is the group of methods we'll explore in this talk. So a group of methods that relies on a probability distribution over your Q function, from which you can sample a Q function. Then given that Q function, you can act greedily with respect to it, which gives you your policy. So let me illustrate how this works on a simple example here. We've got a tree. We start in state 0. We get a choice up or down. If we choose down, we terminate, go back to start. If we choose up, we're faced by the same choice again. If we choose up many times in a row, we receive a reward. Every other choice grants no reward. So this is a task in which you need to make many up actions in order to ever receive any feedback. Let's consider what epsilon greedy would do. Well, at initializations, all states and actions are as good as all other states and actions. For all you can expect is a value of 0. Thus, you do random exploration, and the best you can do is kind of order of 2 to the power of the state size. You'll be choosing 50-50 between the states. It's going to take a very long time to explore even a very small tree. On the other hand, if we were to use upper confidence bounds, then as long as we've got a good probabilistic model, and by that I mean that the uncertainty about states and actions which are further upstream is propagated back to the point of decision making, then we should always find that the action up carries more overall uncertainty than the action down, and we should deterministically pick actions up most of the time. Now, this relies on a probabilistic model of the states and action values, specifically a model of the variances involved. So if we imagine stacking all the states and actions, if we have a multivariate normal model over this only requires the elements on the diagonal to be correct. It doesn't use any other elements. Let's now consider posterior sampling. If we assume that we have a model of this Q function, an adequate model that captures how our beliefs about the different values are correlated, a multivariate Gaussian model with a full covariance matrix, it's not difficult to show, and it's been shown in the literature many times before, that this can also get a polynomial regret like UCB. However, one thing that happens a lot is, this is proven in the tabular case, when people go to apply posterior sampling with deep learning and have some kind of a deep Bayesian neural network with a mean field assumption in it, meaning we only really infer the diagonal part of a covariance matrix. So we have a multivariate Gaussian model which has some mean and a diagonal matrix for the covariance. Now in this case, let me illustrate to you what happens. We're at state 0. Action up, we've got a mean 0 Gaussian with a high variance. Action down, we have a mean 0 Gaussian with a low variance. We could even assume variance tends to 0. What's the probability that a sample from two zero mean Gaussians, that one of these is higher than the other one? Or for any equal mean Gaussians? Irrespective of the variance, you'll be choosing 50-50. The difference of two Gaussians is once again a Gaussian. The probability is greater than 0 is 50%. So actually, getting the diagonal elements of this model right doesn't give you anything. You're exploring uniformly. And indeed, this is, as I shall show you now, this is what happens in a lot of the current implementations of exploration in deep learning. What you effectively end up with is a diagonal model that does no better than random on little toy examples like this. So, the kind of most trivial way people extend probabilistic modeling to deep model-free reinforcement learning is to say, okay, I'm going to learn my Q function estimates using the usual method. And then I'll treat this Q function estimate as an observed value and run some kind of a regression from the state and action to that value, treating the Q value as if it was an observed variable. And then I'll see how good I am at predicting this Q value and use this for exploration. The problem here is the Q value is not observed. It's a conditional expectation. You can estimate it. You may have an unbiased estimator, but you don't actually observe it. So to model it under the standard linear Bayesian model assumptions is fairly meaningless. You have no way to, in a sense, calibrate the uncertainty in that you don't have a fixed data set of these Q values. You just have a data set of many estimates with a very sort of weird noise which comes just from the way you've computed this Q value. Moreover, if you actually analyze the way this method's implemented, you'll find that despite using a linear Bayesian model, it ends up with just a diagonal covariance matrix as its final output. The next bit of work here was by DeepMind. They recognized that getting the diagonal elements right is important and that you can't just directly model the Q function like an observed value. So what they do is they compute a lower bound for the variance. They say that the variance for a given state and action is the expectation of the variance of the reward plus the remaining variance. So it recursively computes the variance by looking at the variance of the rewards. Now, this is a lower bound because on the right-hand side, the variance should be outside of the expectation. So this, in a way, does a Jensen's. Otherwise, this would be completely uncomputable. And once again, this computes variance estimates, not covariance estimates. So this is a diagonal estimator. And yet, as you should see on the next slide, DeepMind were using posterior sampling. So this method of sampling from the Q function density and acting greedily with respect to it with this method. What I introduce later in this talk is kind of my method, Successor Uncertainties, which models the MDP and then analytically derives the Q function. The model of the Q functions it derives is indeed a full covariance model, and it's one of the only ones so far that scale to deep reinforcement learning and large domains without making the diagonal assumption and thus without completely failing on trivial examples. Here we have the two kind of competing methods, UBE and BDQN, run on the tree example we've seen. We've got the black line, which is how we would expect a uniform policy to do. And we see that both UBE and BDQN, the two competing methods I've just introduced, do not actually do any better than uniform exploration. And this is something that was completely unknown before. The authors of those algorithms were happily applying them to complex tasks, not realizing that their improved performance could not have had anything to do with better exploration. And Successor Uncertainties is the only one of these methods that does indeed perform better. Here also, upon seeing this, we also applied this to Atari, because at the end of the day, if the previous methods just rely on seemingly fluke to perform better, we should be able to beat them. And indeed, this is a plot wherein we have Bootstrap, which is an alternative method that actually doesn't make this mistake. We have UBE and plain DQN, so the plain original Mnich 2013 implementation for Atari. And we see that we beat all three of these methods, with Bootstrap being kind of a state of the art, on pretty much all the games. So we beat UBE, I believe, on all but 5 or 6 games out of this suite of 49 games. So actually this little detail of a full covariance matrix and this observation that without one you fail on a tabular example does seem to carry over into the Atari domain. And all of this was done with no more computation than any of the previous methods, in that the method I'm about to present is no more computationally intensive. Okay, so how to get full covariance estimates? One thing we can easily do within reinforcement learning. So let's first assume that each state action pair has an embedding. We can just say it's one hot for now. If we are able to learn a linear Bayesian model from that embedding to the rewards, we can estimate our uncertainty about rewards attained in any given state. Then how do we go from rewards per state to the Q function? Well, if we had kind of a weighting scheme in which we're able to weight each one of the one-hot encodings by how often they appear if you follow a certain policy, then the product of the weight for each one-hot encoding and how often it will appear gives you a prediction of the expected cumulative reward under that policy. So what we do is we move the problem one level down. We're not able to estimate uncertainty in the temporal difference learning process. It's a very hard task. So instead, we estimate uncertainty in rewards and then project those rewards using this projection by how frequent they are under a given policy onto a Q function. Now the projection itself works exactly like normal Q-learning. We say, recursively, how often do I see this embedding if I follow my policy, rather than how much reward do I see. It's just at the most basic level, a discounted state occupancy. How often do I occupy certain states under my model? So here we model the uncertainty about rewards. We do not explicitly model uncertainty about transitions. However, at the end of the day, the kind of prior variance and the observation noise of the linear Bayesian model need not be calibrated correctly for rewards. We can overestimate our uncertainty about the rewards in order to absorb some of the uncertainty about transitions. This is not perfect, but the overall projection, if we have a look at the product of these embeddings and these linear Bayesian model weights for rewards, the distribution thus implied gets us a covariance matrix which is very much not diagonal and corresponds to an assumption about the underlying MDP. It corresponds to almost a generative model where we take the maximum likelihood solution for transitions, just taking their averages, and then taking a linear Bayesian model for the rewards themselves. This is simple. It's not perfect. It doesn't solve the problem of how to do uncertainty estimation in temporal difference learning. But what it does give us is a model that's able to both scale up to large tasks like the Atari domain and not to fail completely on simple tasks when used with posterior sampling in the way that the majority of previous methods developed just within the last year or two do. And in a sense, I've mentioned the importance of the dependencies in the covariance matrix. It's not just that some dependencies are required. The dependencies, in a sense, have to be the right dependencies. So we justify and specify this more in the paper. But for the sake of the exposition, the right dependencies are better than no dependencies at all. You could obviously have the wrong dependencies and do worse than uniform random. So to sum up, exploration within reinforcement learning seems to be one of the hardest remaining problems. We're able to explore one step at a time, but not many of the methods, especially not many of the scalable methods, are able to consider the consequences for learning, not for obtaining reward, of taking action, not just in terms of the immediate consequences, but the long-term consequences. This is a hard, open problem remaining within reinforcement learning and, in a sense, within deep learning, a combination of the two. So most of the previous methods end up with a diagonal model. In the paper, we show exactly why this cannot perform well under posterior sampling. And posterior sampling is thought to be the best strategy for exploration if you do have a probabilistic model. And we introduce successor uncertainties, which is a simple way to get this full covariance matrix with, in some sense, the right dependencies, which performs well both when tested on simple tabular examples, but also outperforms the previous probabilistic models on the Atari benchmark suite. Thank you.
Questions?
So you mentioned that the Thompson sampling should do, or has been observed to do better. And you switched to Thompson sampling, but you also improved your model. So I'm curious, if you do upper confidence bound stuff with your improved successor uncertainties model, how does it perform relative to posterior sampling?
I have no idea, I haven't tested this. However, the main thing is that upper confidence bounds, together with the previous methods, worked just fine. It's more a matter that everyone will develop these methods and then go ahead and run posterior sampling because it's thought to be better in general without noticing that there is, that you can't just simply do that. I haven't tested upper confidence bounds with this. I believe it will perform well, maybe better than the previous methods. The previous methods, for example, BDQN and UBE, UBE gives a lower bound on uncertainties, and BDQN gives uncertainties that can only be described as uncalibrated. So I would imagine will perform better, but I have not tried this myself.
Thanks.
Thank you.
Let's thank David again.